I'm extremely happy to have Vijay Vazirani here talk to us. Professor Vazirani is at the faculty at Georgia Tech and, of course, at the forefront of algorithms and theory research. You guys might know him from his, by now, classic book on approximation algorithms, standard textbook now. And for the past several years, Vijay has been working, or rather has been one of the founders of the fields of algorithmic game theory, which is a field at the intersection of algorithms and economics and game theory. And so I'm very glad that Vijay is going to talk to us about one of his newest research papers. So please join me in welcoming Vijay.
Thank you very much. It's a great honor to be here in this company that's at the forefront of search and a crowd that comes from the very best. So I'm going to talk about the Nash bargaining problem today, and I'm going to relate it to markets. In other words, I'm going to solve the Nash bargaining problems by reducing it to a certain market and computing a market equilibrium there. Everything will be done ground up. Please feel free to ask questions on the way if you like, because it's at the intersection of many disciplines, so not everybody may know everything. So bargaining has been with us since ancient times. Ever since goats were our main possessions. But even today, not in the West, but in the rest of the world, bargaining is an everyday activity when you go out and buy things. But even in the West, when it comes to high-end items, not vegetables on the street, but high-end items, when you want to sell yourself in the job market, or when you want to buy a home, nobody can say what the price should be. And typically, you have to do a big, long negotiation or a bargaining. So it's really a very important part of our lives in one way or the other. And it is becoming more so with the internet. Because, for instance, now you can actually bargain for an airline ticket that you pick up at Priceline. Okay? And that's made possible, of course, by the massive computational power available on the internet, and by having these programs that can negotiate one-on-one with buyers. Okay, so in some sense, we are back to bargaining, even in our everyday lives to some extent. And as you can see, two aspects need to go into study whatever useful we want to do here in terms of solving bargaining problems. Namely, we have to be worried about the strategic aspects of bargaining and about the computational aspect of doing it on the internet. And so it will be correct to analyze bargaining in the by now maybe classic style of algorithmic game theory, which actually is a very new area, but so many people have worked on it that there's a whole lot known already in the last 10 years. And that's what I'm going to do. And the most amazing thing for me, at least, is that algorithmic game theory and market equilibria have given to our field of algorithms completely new issues for study. And these new issues have given rise to really completely new chapters in our field of algorithm design. Chapters that would never have been added had we not gotten these problems from game theory and economics. And that's going to be my main emphasis, because that's what really tickles me here the most in this work. So that's what I'm going to concentrate on. So here's a short history of bargaining. The first formalization was given by Nash in 1950, and that's the one that I will talk about mostly. And his work was done right after Neumann and Morgenstern defined the theory of games in their classic book. This was all done in Princeton and Institute for Advanced Studies. And in fact, both von Neumann and Morgenstern are actually acknowledged in Nash's paper. And just a word on game theory itself, you know that it studies, or rather develops solution concepts, provable solution concepts for negotiating in situations of conflict of interest. And since bargaining is in some sense the oldest situation of conflict of interest, it is no wonder that what Nash started has led to a pretty big theory, which lies really at the heart of game theory today. So, what I'm going to show you is I believe, the first work on initiating algorithms for bargaining. I believe there'll be more to do here. Nash bargaining itself captures this main idea that both players will gain if they agree on a solution. But if they don't agree on a solution, then they go back to their status quo. Okay? And Nash bargaining is a perfect information game. That means there's no lying, there's no holding back information. There is some entity that knows everything about both the players and says what the solution is. So it's not like bargaining where you start haggling about the prices, okay, which may be a lot of fun, and all of that is not present in this particular formulation. So it arrives directly at the correct solution. Okay. Here, let me introduce the definition of Nash bargaining via a very simple example. So suppose we have two players, 1 and 2, and they have vacation homes. One has it on the mountains and 2 on the beach. And they consider all possible ways of sharing their 2 homes. And so we plot their happinesses in a 2-dimensional space because there are 2 people. So this is the x-axis is the happiness of player 1. Y-axis is the happiness of player 2. And for any point here, the vector represents some way of sharing the 2 houses, and the happiness is accrued by the 2 players. Okay, and an assumption on this set S, this is called the feasible set, is that it should be convex and compact. Why convex? Because Nash originally thought of this as randomizations over deterministic choices. So these points are actually not deterministic happinesses, but expected happinesses. And so the convex combination of any bunch of happinesses will also be a feasible happiness. And we'll assume that the set is compact. So in particular, the boundary is part of the solution. And in addition, of course, we have the status quo utilities of the two players. So what if one only has the house in the mountains and 2 only has the house on the beach? Then what happens? So we are given C1 and C2, the utility that 1 derives from the mountain house, and C2, the utility that 2 derives from the house on the beach. Okay, and these are called disagreement point. C1, C2 here, this vector is called the disagreement point. And that is the status quo that will happen if bargaining doesn't happen, is not successful. The question is, which point here where both player 1 and player 2 can both be happier than their disagreement utilities is the right one to choose. Okay, so that's the whole question, and we will always encode a Nash bargaining problem by, or rather define a Nash bargaining problem by defining this set S, the feasible set, and the point C, which is the disagreement point. Okay, so the big question is, which is the right solution? And it obviously has to be in this range, because if you give any player less than their disagreement utility, they'll just say, forget it, go away, I'm gone, and both of them will only get their own houses, right? So which is the right solution? So for this, Nash gave 4 axioms, which are all, well, the first 3 are very reasonable, and everybody buys them. But the fourth one is a little bit more contentious, and I'll say why. So the first one is that the point should be Pareto optimal, which means that it should be on the boundary of S. Because if you choose anything inside S, then at least one player will do better. The second is that the solution should be invariant under affine transformations. Or another way of saying it is that the two people can choose their own units for expressing their utilities. So if player one says, I usually say Bill Gates, but let me say Larry Page. Okay, if player one says I'm Larry Page, and so therefore please multiply my utilities by 1,000,000 and add a gazillion to them. Okay, then all you have to do is take this whole Nash bargaining situation, multiply the first coordinate by 1,000,000 and add a gazillion, and you'll get the solution for the new problem. Okay, that's invariance under affine transformations. Third one is symmetry, which says that the naming of the players has nothing to do with the solution. So if you switch the coordinates, all coordinates, the solution also switches the coordinates. The fourth one is a little bit more contentious one. It's called independence of irrelevant alternatives. You might have heard of it in the context of arrow voting theorems, but I'll say what it is. Let me say it formally first and then give you some examples. So for the moment, assume that the Nash bargaining solution is a unique solution. So given a problem instance defined by a feasible set S and disagreement utility C, let's say that n is a function that gives us the Nash bargaining solution. So the point in S that Nash says is the correct one. So suppose V is the correct solution for SC, and suppose that T is a subset of S which contains V, the solution for the bigger problem. Okay? Then this fourth condition says that in that case, the solution to the smaller problem should also be V. And the reasoning being that all you have done is remove some irrelevant alternatives. And why should that change the solution from V to some other V prime? Right? That's not bought, always. I don't know. I mean, there are many situations one can think of. But suppose suppose I say to Aranyak, let's meet sometime between 9 and midnight tomorrow, 9 a.m. and midnight tomorrow. And he says, OK, 3 p.m. But then say, oh, no. Sorry, I meant let's meet anywhere between 3 p.m. and midnight. Maybe he will not stick to 3 p.m. then. No, because he'll say, if he wants me to come at 3, I'm not going to come at 3. I'll come at 4. At least that's what he did when he was a student. But actually, the best example I found of this IIA, it's also called IIA, was last summer in Sweden. Somebody there mentioned this to me. So there's a guy that goes to the coffee shop and asks for a cup of coffee and says, 1 cup of coffee, no cream, please. And the guy there says, we just ran out of cream, but we can give it to you without milk. So anyway, you can see that it is contentious, and actually people have substituted this with some other axioms and found alternative solutions. But by far, Nash's is the most beautiful solution and the one that really has the most beautiful properties, and the one that I'm going to study here. And algorithmically also, it's the one that really gives rise to the best theory. So far, at least. So here's Nash's big theorem, that if these 4 axioms are ensured, then in fact, there is a unique solution to the Nash bargaining problem, which is the one that's obtained by maximizing this product. So take overall V1, V2 in the set S of V1 minus C1 times V2 minus C2 and maximize. Okay? So the point that maximizes this product in the set S, and that will be a unique one, buy that from me, is the Nash bargaining solution. And all of that generalizes to the case of n players, where the utilities are plotted in n-dimensional space. And then the Nash bargaining solution is a unique one that maximizes this product of these analogous terms for the n players. Now, there may not be any, it could be that C itself is not in S, because S, after all, is some set, and C could lie outside of it. So maybe there's no way to get a positive amount here. So for that reason, let's say that an instance SC is feasible if S contains a point that makes each player strictly happier than CI. OK? So in that case, we'll say that the Nash bargaining problem or game is feasible. And this point should make everybody strictly happier than their own disagreement utility. And then, of course, because if there's no such point, this maximization may not even make sense. It could be over negative numbers or undefined. So in game theory, it is customary to only study promise problems. Games, they always assume that the given game is feasible. Okay? But we know that itself, testing for feasibility itself is an important algorithmic question, and I'll address that in a moment. So I want to define this class, which I call linear Nash bargaining. Yes?
Yeah, I didn't quite understand why the status quo point C when would it not be part of the feasible set?
Can you repeat the question for the second?
Yeah. OK. So the question is, why should C not be a part of S? Because maybe S, C is, nobody says that C comes about by sharing S in particular ways. C may be something else altogether. OK, typically it will be, OK, but it is not always the case. OK.
It's not the intuition is not wrong if I feel that C should be part of this. I mean, the sense.
OK, yeah, OK, so let me say it in another way. Maybe C is part of S, but still there may not be any point that makes each player strictly happier than CI. OK, and that is really needed to make this thing positive. Otherwise, it will always be 0 or negative or something. OK, so let's assume this particular stronger condition. OK.
You just hate mountains.
Sorry, yeah. But he's saying at least C should be in S, which is a more reasonable statement. OK, but even that is not good enough for us. We want this stronger condition to hold. And game theory always assumes that the given games always satisfy this. But for us, that becomes an important algorithmic question in itself. OK, so let's quickly define this class, linear Nash bargaining, LNB, which is the class of all Nash bargaining problems in which the feasible set is defined by linear packing constraints. So by linear packing constraints, I mean constraints of the kind less than equal to, in which all the coefficients and the right-hand side are non-negative. OK? And if so, the Nash bargaining solution is an optimal solution to this convex program, where what I've done is instead of maximizing this product, I took its log so that after I take the log, I get the sum of the logs of these terms, vi minus ci. And I have to maximize this objective function subject to these linear packing constraints, whatever they were. And it's easy to see that this is a convex program. And therefore, the ellipsoid method will come as close to the solution as you want it to, if you give it enough time in terms of the accuracy needed. And that's the end of the story, if that's all we wanted. So let's ask for something more. OK? And what I'm going to ask for more is that the solution should be a combinatorial polynomial time algorithm. OK? And why combinatorial? And what is combinatorial, first of all? By combinatorial algorithm, I mean that it is going to pick a solution from a discrete space. So there are some discrete choices, and it has to home in on the correct discrete solution. OK? So just to give you intuition on this, think of linear programming. You can either view it, you know that the optimum is always attained on a vertex of the polytope. So you can either view it as a discrete problem Namely, you are searching among the discrete vertices to see which is the optimal one. Or you can think of it as a continuous problem, which is approached at via interior point methods or ellipsoid method and so on. So I want to, and actually the findings of these two types of algorithms, discrete or continuous, are quite different. The kinds of intuitions and algorithmic structure that they reveal are quite different. And I want to home in on these kinds of algorithms because I think there are some particular kinds of insights to be gained by studying these problems combinatorially. And I'll give you instances of the kinds of insights. And should we study the promise problem? Well, no, because we in computer science know a little bit better, right? We know that if we solve the promise problem in polynomial time, then the decision problem also gets solved in polynomial time. And so we might as well study the decision problem of whether a given bargaining game is feasible. And if it is feasible, then find a Nash bargaining solution for it. OK. And here is the one main problem that I want to study in the most depth in this talk, which is that suppose that there are n players, and each comes with their own disagreement point. And right now, there are any old numbers declared by the players. Just to make it concrete, sometimes we can think of the disagreement points as being, we can think, OK, so one moment. So besides the n players, we also have these g goods. OK, and we can assume unit amount of each, because we are going to assume that each player has a linear utility function saying how much happiness they derive from an allocation of the goods. So player I, when she gets xij amount of good I, gets uij times xij happiness for this particular good. In other words, uij is the happiness that she gets from 1 unit of the good. And this linear function of the allocation is her total happiness on her entire allocation. If you want to make these CIs more concrete, you may assume that each player has some initial endowment of goods, and CI is I's initial utility for her endowment. Okay. So we are given all these numbers, CIs and UIJs, and now we distribute these goods in all possible ways among the people, compute the utilities that they got from the goods, and that is our feasible set S. And then the Nash bargaining solution is actually the solution to this convex program, which is maximizing the usual thing, subject to just the constraints that there's only at most 1 unit of each good, which I said was without loss of generality. This was without loss of generality because if there's more than 1 unit of a certain good, I can scale the UIJs appropriately and assume that there's only 1 unit of each good. OK, so I have only one kind of constraint, really, because this could have been plugged right back in here, the VIs. OK, so that's a convex program. And we want to solve it combinatorially. OK, now, that seems a bit far-fetched. What discrete objects can we search over to find the exact solution to a nonlinear convex program? OK, and the first ray of hope that arises is if you apply KKT conditions, then it's possible to prove that if the if the whole problem instance is feasible, that means if the CIs and the UIJs are all rational numbers, then in fact the Nash bargaining solution is also rational. Sorry. And moreover, the solution can be expressed using polynomially many bits in the size of the instance. I was trying to drown the other guys, and I lost my voice a bit, sorry. But now I don't need to. So that's the first fact that says that there's even hope of a combinatorial algorithm. But actually, there is an entire algorithm, and I'll show you how it comes about. OK, so the decision and the search problems can both be solved in polynomial time. OK, so The next set of results, and I'm coming back to this problem in 2 minutes and show you a lot about this algorithm. But let me just say the kinds of other results that I can get about this. So I defined this subclass resource allocation Nash bargaining problems inside linear Nash bargaining, where players use goods to build objects, and a player's utility is just the number of objects he builds. Okay, so for instance, in this situation, we have a network with capacities on edges, and we have, let's say, 2 players. S1, T1 is one player, and S2, T2 is another player. Both want to get as much flow as possible. So you want to route as much flow from S1 to T1 as possible, and as much flow from S2 to T2 as possible. But then, of course, there are capacities on the edges. Okay? And let's say that these players also have some disagreement utilities. And here, these are arbitrary numbers. I mean, again, these could be the 2 founders of Google, and each has a number saying, I want at least so much flow. Okay? And those flows may not even be routable, for all we know. Okay? But if they are routable, then the point arises, what is the Nash bargaining solution here? Okay, for instance, for the case of single source and multiple sinks, I can get actually a strongly polynomial algorithm in this case, and the solution is again rational. So, but I don't want to go into these kinds of problems, and I just want to jump back into the other kinds of the first problem, and actually. In a paper that's just getting completed as we speak, actually, we managed to use the combinatorial insights from these algorithms to talk about the efficiency of Nash bargaining solution, which is a notion just like the price of anarchy that you might have heard of. We call it the price of bargaining, and basically that measures the inefficiency of the Nash bargaining solution as opposed to the most efficient centralized solution that somebody could have come up with. Okay, just like price of anarchy measures the inefficiency of Nash equilibrium as opposed to the best centralized solution, here we are measuring the inefficiency of Nash bargaining solution as opposed to the best centralized solution. Okay, then we talk about max min and min max fairness of the solutions of whether people got something that was max min and min max fair, and something called full competitiveness, which says that if somebody increases their disagreement utility, do the other people's utilities go up or down? Yeah.
What relation, if any, does this have to the market clearing problem? Because there also it seems similar, right? And clearly in the solution, no good is going to be left. I mean, because all of them are positive, it's going to sort of clear out. Then you try to put the price and the object
yeah.
as different.
So you're asking what is the relation of this to market equilibria? I'm coming to that next. I mean, it's a good guess. And if anybody read the title carefully, it's the right guess also. So let's talk about that. OK, so again, this is the problem I want to solve, right? This Nash bargaining problem. And here's my game plan for the rest of this talk. I'm going to use KKT conditions to transform this Nash bargaining problem into that of computing an equilibrium in a certain market, and then show you how the equilibrium is computed using the primal-dual paradigm, about which also I'll talk a bit. And the big question next is, what is this certain market? Which market? Okay. So for that, I'm going to change gears in a big way and talk to you about general equilibrium theory. Okay. So what is general equilibrium theory? This was really a very, very central, and perhaps, not perhaps, but definitely the most important theory within mathematical economics for a very, very long time. And the reason for its importance was that in the West we are in a capitalistic economy, so there's no central authority making wise decisions. All the decisions are made by pricing mechanisms, including what should be your salary, what should be my salary, and how much should the laptop cost, and how much should a piece of bread cost, okay? And so thereby how much happiness each person gains in life, something as important as that, is all determined by pricing mechanisms, namely market forces. So the big questions that people had in mind for many years, many centuries rather, was all the way to Adam Smith in the 18th century, was whether or not these pricing mechanisms really make sense, whether they have the power to do the right thing. In other words, achieve fairness, achieve stability, achieve efficiency, and that's why this was a big theory. And one of the central tenets in this theory was that prices should be such that supply equals demand. In other words, the prices should be equilibrium prices. And that's very easy if there's only one good, because you just look at supply-demand curves, and where they intersect is the equilibrium price. And if you deviate from the equilibrium price one way or the other, there'll be forces moving prices back to the equilibrium price. Okay? But that's too simple a situation, one good only. So what happens if you have many buyers, many goods, many desires, many buying powers? Okay? How do you study this business of parity between supply and demand? Actually, very importantly, once you have parity between supply and demand, then you get all kinds of properties for free, like Pareto optimality of allocations, some amount of guarantees of efficiency, and of course stability, because if you have supply equals demand, then nothing needs to change, right? Prices don't need to go up and down, and people don't need to be on a roller coaster every day, right? So these are very important matters. And there was a French economist, Walras, who gave a fundamental model. And about the same time, Irving Fisher, who was a PhD student at Yale, gave another fundamental model. And this is the one that I will study here. And here's Fisher's model for studying the issues of parity between supply and demand. So he says that suppose we have n buyers who come to the market with some money mi each, okay? And there are g goods, and again without loss of generality, unit amount of each. And uij is the happiness that buyer I derives from getting 1 unit of good j. So her total happiness is this linear function of the allocations. And the big question is, what are there prices such that if at these prices each buyer buys an optimal bundle of goods for mi amount of money, then the market clears, which means that the goods are sold to the last drop and the money is spent to the last cent. Okay? And that, of course, if there's such a point, if there are such prices, then obviously they are the equilibrium prices. They are the ones that will ensure parity between supply and demand. Okay? So is there even such an operating point where you will have this kind of stability? Okay? So again, one point to be made clear here is each buyer has a given amount of comes with a given amount of money which she wants to, or he wants to spend completely in the market. Okay, and people always ask me, what if they want to take back a few dollars home? And I always tell them that if any one of them takes any money home, their wife will take it for them and will be gone forever. So they might as well spend it all in the market. Okay, so the money has to be spent in the market completely. Okay, and vice versa. Okay, so the spouses will take it away from them at home. Here is an amazing device that Fisher gave for computing equilibrium prices for the case of 3 goods and 3 people. What it is a hydraulic apparatus with these cisterns, which have just the right shapes that they encode utility functions. And when you fill it with water up to a certain place and let these levers settle down, then you can read off the equilibrium prices here. Okay. And actually, Herb Scarf, who's a very distinguished economist at Yale, he tried to construct this and he failed, even though Irving Fisher had made 2 of these devices, one in the 19th century and one in the early part of the 20th century. Yeah, this is part of his PhD thesis. And then Herb Scarf got some of his PhD students to program up and simulate this device, and that worked. But even though this works, I don't think it'll scale to internet levels. So what we need is a real algorithm. And just to say that real algorithms are rare, very rare in general equilibrium theory. It was almost entirely a non-algorithmic field, even though their questions are entirely algorithmic. Perhaps because they were not the right people to answer such questions, but we are. So, and we have been looking at the theoretical computer science community has been extremely active in this area over the last 8-10 years, and a lot of very nice results have come up. Very quickly, I want to say, while the Fisher market is still fresh in your mind, I very quickly want to tell you what my market will be, my market model will be. Okay, and it is identical to Fisher's market model in every way other than buyers do not have a fixed amount of money that they spend in the market. Okay, each buyer has a lot of money, but each buyer knows exactly how much happiness they want to derive in the market. And once we give them prices of goods, they spend just enough money to get this much happiness. And they do have all the money that is needed, but they spend just enough money to get this much happiness. That's the big difference. Okay? So, and to be completely precise, here's how I define it. So given prices P for the goods, because people's happinesses are all linear functions of allocations, for each buyer, the goods that she can accrue at minimum price per unit of happiness, which is basically what this is saying, because this is price of the good per unit of the good, and this is happiness per unit. So this is the amount of money spent to get 1 unit of happiness, minimize that over all goods, and that tells you the most cost-effective way of getting 1 unit of happiness. Okay, so and these are the goods that she's interested in, and we'll define cost I to be this quantity, which is the minimum price for 1 unit of happiness. And every buyer has a number Ci and wants to get utility strictly bigger than Ci. Okay, why strictly bigger?
Because he already has feasible.
Because of feasibility. Remember how we define Nash feasibility in Nash bargaining? Everybody should have utility strictly more than Ci. That's where this greater than is coming from. And so at prices P, buyer I must spend this much amount to get utility Ci, and I'm going to tell her to spend $1 more to get utility strictly more. Okay, and this one is significant. If you want later, I can tell you if you ask me. Okay, and the question again is to find market clearing prices. So in other words, find prices such that if everybody spends money as given by this formula, okay, then all the goods are sold to the last drop. All the money, all of this much money is spent to the last cent. Okay, so that's what this market model wants. Okay, but the point is that unlike the Fisher model where equilibrium prices always exist, here they may not, and so I can think of a feasible or an infeasible market. I can define a market to be feasible if there's an equilibrium and infeasible otherwise. And here's the theorem that the Nash bargaining problem for linear utilities reduces to computing equilibrium for this flexible budget market, the one that I defined. And more precisely, given a Nash bargaining instance, I can transform it into a market of this kind, such that the Nash bargaining instance is feasible if and only if the market is feasible. And if both are feasible, then X is a Nash bargaining solution if and only if it's an equilibrium allocation. So in other words, if you go out and solve this market for feasibility and for an equilibrium allocation, then you will completely solve the Nash bargaining problem. And that's what we'll do. How much? We are about 10 minutes? OK. So the algorithms are all based on the primal-dual paradigm, which is a very big deal in theoretical computer science. It's a very general method for designing algorithms of all kinds, exact, approximation, and so on. But the point is that all those algorithms were designed in the framework of LP duality because they were trying to solve linear programs. And here we are trying to solve nonlinear convex programs. So we have to go to an enhanced setting with the convex programs and KKT conditions. And just a word on the primal-dual paradigm. It was first given by Harold Kuhn, a celebrated mathematician from Princeton, in 1995. And he called it the Hungarian method. And in 2005, the 50th anniversary of the method was celebrated in Budapest because they were so happy about the name Hungarian method. He called it Hungarian because he was giving it for the bipartite matching problem, which had been studied by Hungarian combinators for 50 years before that. And then in 2006, 1 year after this big celebration, a French mathematician found out that actually Jacobi knew about this method in 1855. Okay? And then Harold Kuhn went around giving this talk. And this last summer, I was in China, and they told me that it was known to the ancient Chinese under this name. Okay. So these are the primal and the dual viewpoints of life. So anyway, 6 years ago, we gave a primal-dual algorithm for Fisher's linear market, which was defined, as I told you, in 1891. And this was the first exact algorithm, polynomial time. And this algorithm also solves exactly a nonlinear convex program, one given by Eisenberg and Gale, very, very famous convex program, and solves it combinatorially. And actually, I don't want to get into more details because I'm running out of time. But what is amazing, and why is this remarkable that there's a convex program that captures Fisher's linear case, is that equilibrium and optimization are completely different kinds of problems. In equilibrium, every agent wants to optimize. And it is most surprising that you can do that via optimizing a single objective function as here. Okay. I just want to say that the idea of our algorithm is to do these primal and dual improvements. Of course, the main difference is that the monies are not fixed here, and they are from a moving target. And the problem is not total. So in particular, I have to solve the decision problem. And this is how it goes. Basically, I do primal and dual improvements, starting with some initial solutions, primal and dual solutions. And each time I test some predicates. If this one triggers, then I know that the problem is infeasible. If this one triggers, then I know the problem is feasible. And I do some more primal and dual iterations to actually get the equilibrium. And once I get the equilibrium, I know that that's a Nash bargaining solution. I don't think I have the time to get into all the depth here about the solution. And I just want to say that the algorithm runs in polynomial time. And finding a strongly polynomial algorithm is a very big open problem, at least in my mind. It'll be really, really great. It'll need some fancy new ideas. Okay, I'll leave it as an open problem. So the most intriguing thing about this whole line of work, starting from 2002 work, is that we are seeing here nonlinear programs which always have rational solutions. If all the input parameters to the program are rational, then they always have rational solutions, which is bizarre because these are properties of a linear program, not of a nonlinear program. Okay, the nonlinear programs had no business doing this. And worse still, they lend themselves to combinatorial algorithms. And who expected that to happen, right? So this was extremely troublesome for a very long time. And then recently, I found a way of reconciling with it by looking at the bigger picture, which basically is the following, that the primal-dual paradigm actually gave us combinatorial algorithms for many central problems in P, like matching, flow, shortest paths, branching, spanning trees, and so on. And in all of those problems, they are solved by solving certain linear programs optimally. And these linear programs have the property that the polytope defining them always have integral vertices. And so the solution to this linear program is always integral. Okay? But a linear program is meant for capturing fractional solutions. Why on earth does it always have integral solutions? I mean, it's the same old problem, right? Then in the 90s, we saw how linear programs are used for getting near optimal integral solutions to NP-hard optimization problems. Okay? And moreover, there are some linear programs whose integrality gap exactly captures the hardness of approximation of the problem. And why did these kinds of very, very accidental and rare things have to happen? So in light of that, we shouldn't be surprised about this either, maybe, this new development. Except that there's one aspect that still bugs me, which is that what is happening here, you saw all the convex programs had a very special form. The nonlinear convex programs, they had a very special objective function, and they had linear packing constraints. And so there are all these very, very good things happening in a very, very small space. Okay? And what it really reminds me of, at least, is the tip of an iceberg on a nice sunny day. Okay? So the question that comes to mind is what does the rest of the iceberg look like? Okay? And or at least I hope there's an iceberg there of which this is a tip. And if so, what is the rest of the iceberg? And here's a guess. And I don't think this is a correct guess. It may not pan out. But it's the best thing I can suggest right now, which is how about solving these convex programs, or a larger class of convex programs, approximately. And that makes a lot of sense here, because if the convex programs don't have rational solutions, then we can still get rational approximate solutions to them. Okay? And this is the kind of jump that happened when we went from here to here, from the blue stuff to the green stuff, because what we did was we adjusted the primal-dual paradigm using approximate complementary slackness conditions to get approximation algorithms instead of exact algorithms out of the LPs. And what is the mechanism that will make us go from here to here, or if this is at all possible? I'll leave that open. And the final question is, these convex programs, including the Eisenberg-Gale convex program and the one for Nash bargaining, their input-output characteristics are just like that of a linear program. Okay? So the question is, can these problems, linear Fisher or linear Nash bargaining, can they be captured by linear programs rather than convex programs? Okay? And I expect the answer here to be no. And my belief is that if this is the space of linear programs, and these are the nonlinear programs, then the convex programs we are talking about are just across the boundary here. And if we can give a proof of no here, then we'll have a great deal of understanding of this boundary. So many people are tickled by this question. I hope we can get some insights sooner or later. So thank you. I've run out of my time also. Yeah.
If you could go back to the schema you have with the flow of the algorithm.
Yeah.
So just to understand this, am I right in assuming that the top right picture, that cycle over there, is kind of your algorithm for the Fisher case? No,
it's a bit more. And the reason is that in the Fisher case, so it's a very good question. He's asking if this is basically, this algorithm is basically the algorithm for Fisher's linear case. And the answer is yes and no. OK, let me say it that way. It is very much like it, the big difference being that money is a function of prices now. So the target is a moving target, okay? But whatever condition comes out of this feasibility is so strong that the moving target is still chaseable. You can still go and hit it, okay? I could have said a lot more about these conditions. There's this entire notion of balance flow, which is very intriguing, which goes into solving this part as well as this part. But it's just, I mean, that'll take another half an hour. So let's call it quits on that one.
So does the Fisher problem reduce to this problem?
To Nash bargaining? No.
To your the Fisher right.
The flexible budget?
The flexible budget.
Reduce. It's a special case. If okay, in what sense is it a special case? Let me just say that. So if we go back a lot, so remember I said here the one is significant. So there is a notion of asymmetric Nash bargaining, where different players have different weights. And if different players have different weights, you plug in here the weight of the player, then the whole thing works out here, okay? And if we just assume that different players have different weights, but their CIs are all 0, that's Fisher's linear case, okay? So in other words, if I take the asymmetric Nash bargaining problem, and then the Fisher's linear case is a special case of that when all the disagreement utilities are 0.
And even combinatorial algorithm, even for the special case, was not known before the 2002 paper, or?
Oh yeah, nothing was known before 2000. Before the 2002 paper, 2002 paper was the first combinatorial algorithm for Fisher's linear case. That's when the whole combinatorial story started. People were looking at convex programs, and but nobody had put 2 and 2 together to say that there's an exact algorithm even using convex programs. So that was the first time that an exact polynomial time algorithm was given. Yeah. Yes?
Is there a reduction in the opposite direction from any variant of Fisher's market equilibrium problem to the bargaining problem?
The two are equivalent. These two are equivalent, basically.
The standard Fisher problem?
No, not the standard Fisher, the changed Fisher. The standard Fisher, no. You're saying from Nash bargaining to Fisher? No, from Fisher to Nash bargaining. Yeah, as I said, yeah, because of this observation. Because of this observation, not to Nash bargaining, but to asymmetric Nash bargaining, which is a slightly stronger version of Nash bargaining. Yeah. Anything? Thank you so much. Yeah.